Hi, everybody. Welcome back. We're going to talk about transforming data a little bit, and we're going to talk about Z-scores, T-scores, IQ scores, and SAT scores. But the foundation is calculating a Z-score. So let's start. As a reminder, we already talked about means and standard deviations, right? So the mean shows you the location of the data set of the score, right? So we're looking for where that score is in the center of the distribution. And then the standard deviation shows you the variability or spread of scores. So now, we have to think about, okay, so we know the mean, we know the standard deviation. How does this individual score compare to a reference group? Now, calculating a Z-scores, you have to know the population mean, population standard deviation. All right. So let's say we had the following distribution. Let's imagine that we had an individual who had a score X, right? X reflects a score, who scored a 68 on a psychology midterm. Another person who scored a 77 on a mathematics midterm, and another person scored an 83 on a geology midterm. The question is, well, which person did the best? Now, if we're looking at the scores by themselves, you're like, well, the 83 looks the best. It's the highest score on the midterm. However, the question should be, how did that person do relative to his or her peers? So the Z-score formula is going to allow us to calculate that. So what I'm going to do is I'm going to stop my share. I'm going to go onto the board and I'm going to show you what the Z-score formula is. And we're going to determine how this person did relative to their peers. All right, so give me a second to set up. Okay, so here we are. I have everything written on the board for us, and I want to go over the formula first. So a Z-score is equal to X, an individual score, minus X bar, the mean, divided by the population standard deviation. Technically, this should be mu because, a Z-score is calculated when you know the population mean and standard deviation. All right, but let's apply it here. So we could do psychology 68 minus 65 divided by 6. Is it clear how I got that? 68 is X minus 65 X bar divided by the standard deviation of 6. So 3 divided by 6 gives me 0.50. So I'm going to put positive 0.50 here. Now, it's going to be interesting. We need to know where they are in the data set. That's going to tell a story. So now let's calculate mathematics. 77 minus 77 divided by 9 equals 0 divided by 9 equals 0.00. So we're going to put that here, 0.00. And then we're going to do the last one, which is geology. 83 minus 89 divided by 8. So 83 minus 89 equals minus 6 divided by 8, or minus 0.75. Okay, so 0.75 in the negative. So we have our z-scores calculated. For psychology, it's positive 0.50. For mathematics, it's 0.00. For geology, it's minus 0.75. By doing this, we can actually suggest counterintuitively that that individual who got a 68, which was the numerically lowest score, actually did the best relative to their reference group, because this mean is the class average, right? So this person scored better than average. And the other thing I want to do, forgive me for turning my back to you, is talk about something called the bell curve, the normal distribution, right? So in the center, we have a 0, right? And then we have +1, +2, +3, -1, -2, -3. Okay, so now I've done my plotting of the bell curve. Sorry, I left your frame. I could actually plot psychology, math, and geology on here. Watch this. Okay, so I've plotted geology as minus 0.75, math as 0, and psych as 0.50. And if we're going to look at percentile rank, we follow it this way. So the mean, remember, if in a normal distribution, the mean, median, and mode should be the same. So this is the 50th percentile. So actually, psychology is up here. So similar to what I said, people actually did better in this example in psychology rather than math and geology. So I'm going to go back into the lecture and teach you some of the basic principles, some of the other principles, and then we'll come back to the board. All right, so here's where we left off. We now know the answer to this question, right? So psychology had a z-score of 0.50, mathematics had a z-score of 0, and geology had a z-score of minus 0.75. So on the surface, as I said, it looked like psychology did the worst and geology did the best, but it was actually the reverse. Psychology did the best and geology did the worst. So why am I telling you this? Because when we think of z-scores, it gives you a more accurate portrayal or representation of how a person did relative to their peers. And that's the point. So looking at a raw score, whether it's a mean or a standard deviation or an individual score, that in of itself is meaningless unless we can compare an individual relative to their group. All right, now, one challenge we have is comparing across scores. If we don't have the same means and standard deviation, it's tough, right? So if you don't have the population standard deviation, you can't do this standard z-score formula. So you need to have this information. We could also turn the formula inside out and start with a z-score and convert it into a raw score. Now, here are some general rules or principles similar to what we talked about in our first lecture, right? So when we get the mean, remember, if you add or subtract by a constant, the mean increases or decreases by a constant. That we said in our fourth lecture and was evident in our first lecture's rules. If you multiply or divide by a constant, the mean will be a multiple or a dividend of that constant. Whereas with the standard deviation, if you add or subtract to every score, the standard deviation does not change. But if you multiply or divide, then it will impact it. All right, so here's the general rule. As you saw on the bell curve, right? We treat the mean as 0. And we treat standard deviations as units of 1. So +1, +2, +3. Remember that bell curve I did. -1, -2, -3. So the mathematical theory behind it, and it makes, if you're not into mathematics, it may not make much sense, but it is the formula. So for the mean, we subtract the old mean by itself. So if you subtract any number by itself, you're always going to get 0. The standard deviation, if we divide the old standard deviation by itself, any number divided by itself is 1, right? So, except for 0, that's an illogical process. And if you want to hear something funny, go into your Siri and ask her what is 0 divided by 0. But I said we can calculate a z-score. I demonstrated that. But we can also calculate a raw score. And a raw score is X, that score is equal to whatever your z-score is times the standard deviation plus the mean. So this formula is going to be important for calculating raw scores when the z-score is known. So I'm going to put some numbers on the board, and I'm going to see if we can calculate some raw scores. So let me set that up. All right, so here we are again. Let me make the camera in focus. So the first thing I did was I wrote the formula here for calculating a raw score when the z-score is known. So a raw score is equal to the z-score times the standard deviation plus the mean. And I put 2 examples up here for us to work through to show you how it would work. Now, again, the mean and standard deviation must be known. Remember, we said that earlier in the slideshow. It's impossible to calculate this without it. So it's z, which is 1 times the standard deviation of 5 plus the mean of 10, right? So you see the formula z, which I found here as 1.0, times the standard deviation, which is 5, right? Plus the mean, which is 10. So 5 plus 10 gives me a raw score of 15. That would be my raw score. All right. Now, let's do it again with example 2. So here we have a z-score of 0.5, 0.5 times the standard deviation of 10 plus the mean of 30. Okay, so 0.5 times 10 is 5 plus 30 gives us a raw score of 35. So look, the biggest point I'm trying to teach you is whenever we want to calculate a raw score, right? X is the raw score, the individual score, was equal to z times the standard deviation plus the mean. So here are 2 examples how I calculated it. So far, if we're keeping score, you have 2 formulas. We're going to have a couple more, but give me a moment. I'm going to set that up and we'll calculate that as well. So I'm going to go back to the slideshow and we'll go from there. All right, so here we are. The other scores we have to calculate are T-scores, IQ scores, and SAT scores. So in general, this is going to be crucial. We need to know the mean and the standard deviation for each of these. So a T-score, if we're going to transform it, we need to know a T-score's mean is 50 and its standard deviation is 10. We're going to go through other computations. An SAT score, we need to know that the mean is 500 and the standard deviation is 100. And an IQ score, we need to know that the mean is 100 and the standard deviation is 15. If we know that, then we can calculate, pardon me, the slide just jumped. If we know, again, it jumped. If we know that, we can calculate anything. So what I'm going to do is I'm going to take the computations from the slides, set them up on the board, and we're going to do it manually. So in order to calculate a raw score, what did you need to know? You needed to know the Z-score, you needed to know the mean, you needed to know the standard deviation. These three examples are pretty straightforward, right? So we are going to know the mean, standard deviation, and Z-score for all three when we get to the board, and that should allow us to be able to calculate. All right, so let me stop my share, set up the board, and I will be right back with you. All right, so here we are. On your slides, the first slide on T-score was, well, what would the T-score be if we had a Z-score of 1.26? No problem. So we plug in our T-score formula. So T equals 10Z plus 50, right? So that's a Z. So 10 times 1.26 plus 50 gives us 12.6 plus 50, which gives us a T-score of 62.6. Now, you're probably like, well, where did these numbers come from? Well, we know the mean and standard deviation for T-score, right? I already talked about that in the lecture. Mean is 50, standard deviation is 10. This I gave you. I threw out the number, gave it to you. So when you have that, you just plug that into the Z. Now we can do the IQ score, right? So IQ was equal to 15 Z plus 100. And on your slides, I asked you, well, what would the IQ be if I gave you a Z-score of 1.25? No problem. So we do 15 times 1.25 plus 100. Okay. So what is 15 times 1.25? Well, if you're not sure, go back to your calculator, as we always do, and you do 15 times 1.25, and you're going to get 18.75. So we're going to do 18.75 plus 100, which gives us an IQ score of 118.75. So now I've calculated a T-score, an IQ score. The only one left is the SAT score. We know SAT is equal to 100Z plus 500. Okay, so what would the SAT score be if the Z-score was positive 2.0? So we would do 100 times 2 plus 500, which would give us 200 plus 500, which would give us 700. Now, obviously, this would be a section score, but I have everything on the board. I'm going to lower it a little bit so you could see everything in frame. I taught you the formula for a z-score. I taught you how to calculate a raw score. I taught you how to calculate a t-score, an IQ score, and an SAT score. So, general principles, pulling back. To calculate any one of these, you need to know the mean, standard deviation, and then the z-score. So all four of these formulas, you need the mean, standard deviation, and the z-score. And that is basically today's lesson. I hope you enjoyed yourself. I hope it's pretty straightforward. We're going to continue in this lecture series, but as we move forward, we're going to start to need the appendices in the back of the book, and that will allow you to calculate different things like critical values and things like that. But I'll explain that when I get there. So for now, let's put a pin in it there, and I'll see you next week. Take care, everybody.